Good morning, distinguished guests, ladies and gentlemen. Welcome to join us at the Laureate Lecture of 2024 Tang Prize in Sustainable Development. I'm Angela Liu, your MC for today's event. To begin with, we would like to invite to the stage the host of this lecture, Professor Liu Zhaohan, academician of Academia Sinica, to give us the introduction. Please welcome Professor Liu.
Distinguished guests, ladies and gentlemen, it is a great honor for me to introduce the 2024 Tang Prize for Sustainability, the laureate, Professor Omar Yaghi. He is the speaker for today. Currently, he is the James and Neil J. Tratter Chair Professor of Chemistry at UC Berkeley. Professor Yaghi established a new field in chemistry, the reticular chemistry. It leads to new ways to make ultra-porous metal organic frameworks as well as covalent organic framework. Professor Yaghi has demonstrated that these new classes of materials can be tailored for carbon capture, hydrogen and methane storage, as well as harvesting water from desert air. These, of course, will help us build a sustainable future for our planet. Today, Professor Yaghi will talk to us about how the basic science of this new field was established and how this technology was taken from the laboratory to the practical field. He will talk to us on ultra-porous crystals for a sustainable future. Professor Yaghi, please.
Thank you, Professor Liu. Please take your seat.
Thank you, Professor Liu, for your kind words and for that great introduction. I am delighted to be here, and it's really an honor and a pleasure to accept the Tang Prize for Sustainable Development. It's been really a very nice visit to this beautiful place, and also very nice to interact with very hospitable people, including those of the Tang Foundation. So I would like to share with you some of our work and how we discovered and developed ultra-porous crystals that have turned out to be very important in many aspects pertaining to building a sustainable future. First, I want to just state what the problem that I want to talk about is. And one is that carbon emission is causing havoc in our planet. It's heating our planet, it's acidifying our oceans, and it is causing extreme weather events, both in ocean and on land. These are affecting our lives and our livelihoods, especially in the developing world. I've never heard of heat domes until recently, and we've had many of them in the United States. Every year has been a record heat year in recent times. And this is especially scary for me because I used to have a small place in Malibu, and most of Malibu in that area has burned back in 2018. Almost 2 million acres in California burned that year. So it's a very serious problem, and it's coming closer and closer to where we live, and it's affecting our daily lives. There's another problem. That's the problem of water. This map shows in increasing shades of red the seriousness of the problem. 1/4 of the world will experience water crisis, not just stress, but crisis by the year 2040. Even places like Taiwan, Belgium, England, Midwest of the United States, these are places that we think are highly watered, will be in a water crisis because we're using too much of the underground water or because of the patterns of rain. So never mind the arid parts of the world, it will become even worse than it is today. So you can see a lot of red on this map, and you can see the progression of red spreading from now until 2040. Today, almost 1/3 of the world experiences water stress for most of the year. And by the year 2040, almost 5 billion people will experience water stress, and 1/4 of the people living on our planet will experience the crisis. So this is a serious problem. And closer to home, you can see here, if you go to Las Vegas, you should visit the Hoover Dam. The Hoover Dam is in Arizona, next to the Nevada border, and back when I was a student in 1983, this was the water level. And in 2003, it was here. And 2022 is here. It's very clear that there is a major decline in the level of water in this important dam, which is supposed to supply 16 million people with water. Okay? This is really scary. This is alarming. So this is the end of the bad news for today. Okay? Now I will give you the wonderful news. The nice news is that we know the molecules that are responsible for a sustainable future. These are some of the smallest molecules known in chemistry: hydrogen, methane, carbon dioxide, and water. Because they are small, they're very difficult to control, okay? And if we can control these, For example, hydrogen, if we can store enough hydrogen at room temperature, we would have solved the clean energy problem, okay? Carbon dioxide, if we can extract carbon dioxide from the air selectively or extract it from flue gas of power plants before it reaches the atmosphere, we would have cleaned the air and addressed the climate problem. If we can extract water from air, we could make drinking water. So we know the cause of the problem. And as scientists, the minute we know the cause of a problem and there is a will of society to address the problem, it will be addressed. And that's what I want to show you today. I want to talk about carbon dioxide, and I want to talk about how we can clean the air from carbon dioxide and obtain clean water from air. It sounds like magic. It's not magic. It's really true. Okay, it's real. It's real. So chemists know how to navigate this periodic table. And for the last 100 years, they've been using this periodic table to make molecules, such as drug molecules, pharmaceuticals, right? That's a major contribution over the last century. We have developed a way of taking those molecules and L molecules that you know and putting them together in ways that no one has ever done before to make a large class of materials. Let's say an infinite class of materials with infinite number of possibilities and infinite number of applications. Today I'm going to emphasize the climate-related applications and sustainability. So these materials, they appear to the eye like baby powder or sugar, okay? And if you zoom in to the atomic level, as this movie will show shortly, you will see that they're made from hubs and struts, exactly like a scaffolding, okay? You zoom in on one granule, and you can see very clearly the hubs that are connecting these struts to make a framework, an open framework, into which gases, like the ones that I have been describing, hydrogen, methane, CO2, and water, can be incorporated into the pores. So this is a new way of managing these gases and making it possible for us to control them and address the sustainability problem. On the basic science level, the question that we wanted to address was never asked before, in that what happens when molecules interact strongly with each other? What happens if I start taking molecules and stitching them together by strong bonds? That's what we need to do to be able to make these housings, molecular housings of gases. Well, what happens if you're a student back in the 1990s in my lab, you would have gotten something that looks like this, and the physicists and chemists and material scientists in the audience will recognize this is a mess, right? This is really a mess. There is no order to it. You can do absolutely nothing with this. So this is why most people shied away from this area, because we wanted to make something as crystalline and as ordered as diamond. We wanted to make crystals. And diamond puts carbon atoms in an array, in a periodic array. This periodic array is what gives diamond its beautiful properties. So can we take molecules and put them together as they would be in diamond? Well, you need to know how to crystallize materials. Now, it took nature billions of years to make diamond under geologic pressure, geologic time scale, and geologic temperatures. We want to do this in a much shorter time scale. We want to do it within the day, hopefully. So let me explain how we were able to address this crystallization problem. So how do crystals form? Our idea was take building units, take metal ions, and link them with organics. The organic is the strut, and the metal ion forms the hub. Well, notice then that when they come together, it's kind of random. They're not very well ordered. And to make them ordered, you need to control their interactions. You need to find the chemical conditions under which to allow them to combine together and fit together like a jigsaw puzzle. That's not easy because molecules have their own mind. So we have to coerce them and to go against the will of nature to put them together as precisely as you would, with a jigsaw puzzle. Okay, so this is our ordered system, and this is the way these assemble to end up into order. All the chemistry that we developed had to do with how to turn this chaos into order. Okay, and that has to do with controlling the kinetics and thermodynamics of crystallization. And thereby, we have invented a whole new area of chemistry that goes from what people have been looking at, supramolecular chemistry, which is the control of weak bonds between molecules, to the control of the strong bonds, and be able to crystallize frameworks like the movie I just showed you, metal organic frameworks and covalent organic frameworks that are held together by extremely strong bonds, some of the strongest bonds known in chemistry. And thus the birth of a whole new field of chemistry we call reticular chemistry. And I define it as the chemistry of linking molecular building blocks by strong bonds to make crystalline extended structures. Science is relevant to solving societal problems, okay? We want the molecular building blocks because we want to control the materials on the atomic molecular level with precision. We want the strong bonds because we want the materials to be in a power plant for years, not just a day or two. We want them to be there for years without having to be replaced. They need to be stable, and for that stability, we need strong bond, and we need them crystalline like diamond so that all the environment inside the material is homogeneous and it can behave in the same way every time you do a cycle of carbon capture and release. And so the result of this chemistry has been MOFs, metal organic frameworks, and the yellow ball indicates the space within which gases can be incorporated, and COFs, these are all organic compounds that we reported back in 2005 and 2007. And I won't talk about this, but we can also, to indicate the sophistication with which we can control matter on the atomic molecular level, we can also weave, just like in clothing, we can weave on the molecular level in order to transform the mechanical properties of materials. So this chemistry goes beyond just trapping gases in the material, but you can also use them to make mechanically robust materials. So this is how you can do it. It's quite simple. You take a solution of this strut and a solution of what would be the hub, and you put them together under these conditions. These are conditions that organize it like it would be organized in diamond. Make a periodic array, ordered array, and you make what we call a crystal structure here. This is what, if your eye can see on the atomic level, it would see this connectivity. These are the hubs and these are the struts, and this is just a fragment of the much larger structure that extends infinitely. Well, when we discovered this, we knew we had something really important. But we appreciated that importance when we measured the porosity that this framework encompasses. It turns out that the material has about 3,000 square meters for each gram. Okay, think about how many square meters is your apartment? A big apartment. This is a lot more than that, 3,000 square meters. This is as much as a football field for each gram. And so really the inside of the material is much larger than the outside by virtue of the way we have designed them. And in fact, when we reported that footage, that surface area, colleagues at BASF, a chemical company that we later developed a collaboration with, revealed that he said that the number was so unbelievably high, I thought it had to be a misprint. And that began a really nice collaboration with BASF. Back in the early 2000s, we were able to scale these materials up to multi-ton quantities because of this collaboration. Let's just look deeply into one of these crystals, experimentally. Let's just go zoom in with X-ray diffraction to find out why do they have such a high surface area. Okay, here's one crystal, okay? Looks like diamond, but a cube. Okay, this now is evacuated. There's nothing in the pores of this material. Okay, so 60% of this crystal is open space. Okay, it's just drilled holes and there's nothing in the holes. When we do X-ray diffraction on this, we find the framework is maintained and there's absolutely nothing in the pores. Okay? So that means that the structure is architecturally robust. Okay? It doesn't collapse when it's empty. And that's important for the applications that I will discuss. But we also found when we introduce small amounts of gases into the pore that they sit in very specific places on the hub and on the strut. In fact, everything that you're looking at in a MOF structure is an adsorptive site. It's a site onto which you can store hydrogen and gases like methane, carbon dioxide, and water. That's why they have extremely high surface area, because the accessible surface is every atom that the structure makes up. And so using that thinking, after that finding, we realized, okay, well, you have to increase the size of the linkers and the size and the hubs, and so everything you're looking at in this structure is open, and so you can then increase your surface area, more than double your surface area. Now your footage is 6,400 meters square for each gram. Okay, so again, the accomplishment here is that you can take a sugar cube, which might have a surface area of 1 meter square per gram, and expose its interior by virtue of our design strategy, expose each atom so that it's a surface to make materials now up to 7,000 meter square per gram. So we open the door on a gold mine of new materials, not just a new way of making materials, but a new way to also modify them, modify the size of your strut, the length, the functionality, the connectivity, the multi-metallic unit or the hub. You can vary the metals, you can vary their connectivity, and you can also tailor the pores in such a way that you can tailor the pores so that the environment inside the pores can be tailored towards a specific application. So we have an infinite frontier, almost an infinite number of structures, and hundreds of applications dealing with sustainability, biotechnology, and medicine. So it was important to take this to the next step, which is let's see if these materials could be scaled up. And BASF a while ago built a plant that produces tons of MOF. This is one of the MOFs. You can see that they are, to the naked eye, they appear like an ordinary powder. But if you zoom in on a granule, as I did with that movie, they're full of, each granule is full of billions and billions of holes into which you can stuff small molecules like hydrogen and carbon dioxide. So let's see how we can solve the carbon dioxide problem. This carbon problem is divided into two parts. The first part is, could we trap CO2 from air? Okay? The amount of CO2 in air is almost double what it used to be before the Industrial Revolution. A baby born today will be breathing almost double the amount of CO2 compared to a baby before the Industrial Revolution. So not only it's harmful to the environment, but it's harmful to also humans, and so our health. So the other part is that we need to trap CO2 from point sources before it reaches the atmosphere, such as power plant. If your power plant burns methane, that power plant is emitting 5% CO2 of its by volume, and if it's burning petroleum, you're emitting much more, 16%, okay? So this is the problem stated in numbers. Now, to someone like me who wants to develop a solution, we have to worry about, well, what makes a good carbon capture material? You want a material that has high capacity. It takes voluminous amounts of CO2 in so that you don't have to do too many cycles. You want something to pluck CO2 out of the air and not take in other things that would occupy space inside the pores. You want the material to be water stable because water is everywhere. And should be also stable to oxygen because also oxygen is everywhere. It should be cyclable. You need to be able to do hundreds of thousands of cycles without the material breaking apart. Now you can see where the strong bonds and the robustness comes in. And you need to be able to take the CO2 in, and when the pores are filled, you want to take it out either by heating or by vacuum, but you don't want to spend too much energy doing that. So you need to have lower regeneration temperature, and it needs to be scalable. You need to be able to make it in multi-ton quantities. These are very important requirements, and it's a tall order for a chemist, material scientist, or engineer to achieve. That's why today, there are, among all the materials that have been investigated for carbon capture, there isn't a material that satisfies all those requirements. And so we are behind in carbon capture. But what I want to show you today is some early evidence using MOFs and COFs that completely change the equation because of the robustness of these structures and the way they handle carbon dioxide. So without going into the technical details, the real experiment that indicates whether you have a good material or not is this one. You put your MOF in a tube and you expose it to air. Here's the air at 420 ppm, okay? And then you look at on the other side. If the other side doesn't have CO2, then your material is great at capturing CO2. Very simple. That's what you want to do. You want to scrub the air from CO2, or this could be flue gas from a power plant. You want to scrub it. And so here's a MOF that we made. It's an amazing MOF, okay? It's made from zirconium hubs linked by a simple organic linker, and it's decorated, as you see here, these green units. The pores are replete with these units, which are amines, okay? In this case, glycine. This amine is placed there intentionally, and it would be the molecule that will extract specifically CO2 from air, because CO2 reacts with this amine. Okay, and because the structure has open pores, the CO2 can go into the pore and attach itself to the amine, and thereby you've scrubbed the air. We also found that, in fact, you don't need to avoid water. In fact, water, for chemists here, shifts the equilibrium towards bicarbonate and carbamic acid. And if you don't have water, you will have carbamate, and carbamate require 2 amines for each CO2. 2 amines capture 1 CO2. But in the presence of water, 1 amine captures 1 CO2. So this was a very fortunate discovery. Okay, so here's the experiment. Our tube is exposed, a tube of MOF is exposed to 400 ppm of CO2, and as soon as it hits the material, the amount of CO2 coming out goes down to 0. It captures the CO2, absolutely beautiful. There's nothing like it. And in the presence of a humidity, it stays in the pore until the pores are completely saturated and then breaks through on the other side. The capacity is about 1.2 millimole per gram. For a commercializable material, you need at least 1 millimole of CO2 per gram. We are over that. And you need the material to cycle 100,000 cycles. Regardless of the cost of the material, if it can cycle 100,000 cycles, and it has a capacity of 1 millimole per gram, it's commercializable. Okay, so what did we do next? We started scaling the material to kilogram quantities, and we started cycling. We cycled 10 cycles, beautiful results, no change in the behavior of the material. 100 cycles, 200 cycles, 300 cycles, we were very happy about the performance. But at 500 cycles, the material decomposed, broke apart, because it's not stable in base. It's not stable in those amines. It's stable in water and acids, but not in those amines. So I'll show you how we solved that problem shortly. But before I go away from this, I want to say that in terms of capturing carbon dioxide, not from air, but from power plants and cement, in this case cement, that problem is already commercialized. So CO2 from cement plants has been commercialized with a MOF that was made in Calgary by my colleague George Shimizu. The capacity is 2 to 4 millimole carbon dioxide per gram, and it's been cycled as of 2021, 450,000 cycles. This is a big development. It's a blockbuster application, and it's now deployed in several cement plants in Canada, trapping CO2 before it reaches the atmosphere. Note here that the flue gas of cement has 14 to 35% CO2. And BASF, back in October 23, announced their partnership with this company and the scaling up of this MOF to 100 tons scale. And it's being deployed, as I said, in those cement plants. Okay, so the problem of capturing CO2 from flue gas that has a lot of CO2, that's solved. I just showed you, it's commercialized. Now we need to solve the problem of taking it out of the air and from flue gas that has smaller amounts of CO2. And for that, we designed COFs. We designed materials that have the same strength of bonds as in diamond. And that's shown here. This in itself is a major development in chemistry. And you can see the stability of the material is unchanged even under the most corrosive conditions, much more corrosive than flue gas or the atmosphere. So I'm very happy to report that, in fact, these frameworks are ideal for capturing CO2 from air. And so here's the backbone of the material in pink and blue. And then we introduce amines. These are the things sticking into the center of the pores. And CO2 comes in and it attaches itself to these blue regions. These are the amine units. Okay, let me show you now a real life experiment. Okay, this experiment takes a tube of this COF, which is a powder, and exposes this to air in Berkeley, okay, where I work. Here's the CO2 concentration in Berkeley air. Okay, it varies slightly, but it hovers around 420, 430 ppm. This is the relative humidity in Berkeley during the days of the experiment. And this is the CO2 uptake. The beautiful thing about this is that the CO2 uptake scales with the humidity. When you have higher humidity, you take up more CO2. Remember, because of the equilibrium, it's shifted to those 1-to-1 ratio of CO2 to amine. And the material does not decline in its behavior. When you look at this point versus a point equivalent to it over here, it's exactly the same uptake. So this material has gone through 100 cycles with absolutely leaving no imprint on the material. The carbon dioxide problem, DAC, direct air capture, is solved. Okay? The capacity is 1.5 millimole of CO2 per gram, above and beyond. So the scientific challenge that has been long-standing of capturing CO2 from air is solved. And the same material can be used to capture from flue gas with even better performance in terms of capacity. So what remains is to scale up this COF. It shouldn't be possible, it shouldn't be impossible, because COFs are made from very similar components to polymers. They're all organic, okay? And organic chemists never failed to scale up a material that they want. That's a very mature field. So once we scale this up to ton quantities, you don't even need to design the device that this material will go into. These devices already exist, but they have inferior materials. So all you do is you replace those materials with these new materials. Okay, so it should take us at least another, I would say, 6 months to a year before we get to this ton quantity of COFs. Okay, so this is a real problem. Chemistry, science has come, and we solved it. Now we need to scale it, and we need to basically commercialize it. So now I go to the water problem. The air at any one time contains almost 13,000 cubic kilometers of water. That's much more than we have in rivers on our planet. There's plenty of water in the air. If I was to give each one on our planet 50 liters of water, I would have only used less than 0.01%, okay? 1/100% of the water in the air. So there's no risk of drying the air if we start using air as a source, as a new source of water, which I will show you how we have been able to do that. And it's recyclable. We don't destroy water. Water doesn't get destroyed, just used and then reintroduced into the atmosphere or into the environment. Why is harvesting water from air so challenging? This can be revealed in examining a psychrometric chart. This chart is a plot of how much water is in the air in grams per cubic meter of air versus temperature. And I've colored the watered areas in green and the arid areas, roughly the arid conditions, in brown. And let's say I'm in a city over here, usually a Mediterranean city like Granada or Rome, would be about here. Okay, humidity 20% and temperature 30%. For me to get the water out of that air, I must cool down the air down to 4 degrees Celsius. That's refrigeration temperature. That's very energy intensive. You're not going to make economically viable devices based on this kind of direct cooling. But let's imagine, let's go back to the movie I showed you. Let's imagine that that moth could be programmed to pluck water out of the air and compact it into its pores. Okay, so that you're building a water structure, almost chunks of ice at room temperature inside the pore. And then I take this moth that is filled with water and I put it in a container. I close that container and expose it to sunlight. The interior of the component of the box or the compartment will heat up, water comes out of the pores and condenses. So now I have created a humidified environment, and in so doing, I only need to decrease the temperature by a few degrees to get the water out, okay? Much easier to take water out of humid air than out of dry air. That's exactly what we have been able to do. So here's a moth. I won't describe it, but here's a crystal structure of a moth that is ideal for taking water out of the air. And it's a movie that I'm going to show you. We're going to extract one of these pores out and slice it and show you where each water molecule resides. Okay, and notice that the very first water molecules sit in the most hydrophilic region. And when the hydrophilic region is filled, is saturated, there is next to it hydrophobic region. So really the interior of the moth is a grid of hydrophobic, hydrophilic, hydrophobic, hydrophilic. When the hydrophilic pockets get filled, they bridge over the hydrophobic regions. And so this pull-push of the hydrophilic and the hydrophobic allows you to control the temperature at which water could be evolved from the system. And so I'm going to show you a movie of that. This is a result of X-ray diffraction analysis. So we know exactly where all the atoms are located. And the first water molecule goes into the hydrophilic regions, okay, 3 regions. Then it fills up the hydrophilic region. Now it bridges over the hydrophobic region, okay? And it does it in a cooperative fashion, just like oxygen in our body going and interacting with the hemoglobin, binding to iron. The first water molecule is a seed that allows you to have a cooperative bonding with other water molecules in the atmosphere and bringing them in. Okay, and that's how the pores get filled. Now I have contained water in small volume, and it's almost chunks of ice inside the nanopore of the material. So this works so well in the lab that we wanted to test it in the desert. So the students took it to Death Valley and made a device you see here. It has pancakes of moth. During the night, they're exposed to air. They take up water out of the air. During the day, they close it, and it heats up, and you can harvest the water, okay? This device is no bigger than a briefcase, okay? And already you can see droplets of water that are being harvested. No energy input aside from ambient sunlight, okay? No one has managed to do this ever in the history of humankind. But these new materials are able to take what we call magic and bring it into the realm of reality. And if you like Death Valley as much as I do, you can see here this what is called the if you have a chance to go there, you would love the view from Dante's view, and that's where the students put the device. You can see this is Dante's view of Death Valley. Very beautiful, very courageous students. I truly admire their initiative and their hard work. So the water is the water is ultra pure. It's the cleanest water you'll ever have, okay? Because the MOF itself is a filter. It's a molecular filter. We tested the water for any contaminations dealing with organics or metals, none whatsoever. That's why the student drank it. And it's not that delicious because distilled water. For you to drink it, you need to mineralize it, make it more tasty. But here's the next level prototype. Now, we electrify the system so that we can make more water. So in this device is equipped with 200 grams of MOF, and it gives you 5 liters of water per day. And it works on the same principle I just described. Air goes in, water goes into the MOF, you heat up the MOF, water comes out, it condenses. There are puddles of water at the bottom. And then you can collect it and drink it. This device is no larger than a small microwave oven. And it could fit in your kitchen with the other appliance, with your coffee maker, okay? And it gives you 5 liters of water every day for at least 6-7 years without having to replace the MOF or anything else. 200 grams of MOF, okay? So this is, to me, this is very exciting because now we're beginning to see that perhaps each one of us could have one of these devices, either devices that are attached to electricity or devices that run on ambient sunlight. Okay, if you want more water, you just use more MOF. Okay, if you use 2 kilograms of MOF, you can make a system like this, which is as large as a small refrigerator, and it delivers 22 liters a day, every day for 6 to 7 years. And then, if you're a chemist like me and know how to manipulate materials on the atomic molecular level, if you insert 2 carbon atoms almost surgically into the strut, then you could take up even 50% more water without changing anything else about the material. Okay, so that's exactly what we did. We used this strut, slightly longer, and you can take up 50% more water. Cyclable. That means that in a device that deploys this material versus the old material, 50% more people could have water. Or you could have 50% more water to garden, to do your gardening. This is the latest device, which we've done in collaboration with GE. This delivers 120 liters per day. This is less than 2 kilograms of MOF, okay? So, what about, okay, how much energy? These are all electrified. How much energy is this going to cost us? As of today, the thing that is costing you energy is the blower, the controls, and the pump in the system. That is 0.2 kilowatt hour per liter. A kilowatt hour, if you are in Arizona or Arkansas, is cheap, $9. In California, it's 9 cents. California, 19 cents. But that gives you an idea of how much energy per liter of water you're using. This is 0.5 kilowatt hour per liter. Let me make it simple for you. If you have 1 ton of MOF with no energy input, you're going to deliver 3,000 liters of water per day, every day for 7 years without having to replenish, replace, or maintain the MOF at 1 cent per liter. Okay? If you have 1 ton of MOF in an electrified system, you're going to deliver 60,000 liters of water per day at less than 2 cents per liter. Okay? So, and recently I discovered that we have a way of harnessing all the heat of the system and reuse it. And in fact, this 2 cent goes down even further per liter. Okay, so that's all from the energetics of the system. That's how much the system will cost you in delivering per liter of water. So this was a headline recently: global fresh water demand will outstrip supply by 40% by 2030. What I want to emphasize here, this is not a problem just for my country, my native country, Jordan, which is an arid area, or Mediterranean region. This is a problem that is all over the world. Every region of the world will experience demand of water and will experience stress. And so if you take our old MOF just for fun, you can see that even with the old MOF 303, that even in the driest deserts of the world, at the driest time of the year, harshest time of the year, you're still delivering water. This is about 7 liters of water per kilogram of MOF per day. Okay, and you can get more in Mojave Desert, which is one of the driest deserts in North America. This is Lanzhou, which is in the western China, Kabul, Riyadh, Baghdad. You see in Riyadh, you can get about 36 liters of water per kilogram of MOF per day, every day, for up to 6 to 7 years. Same thing, you can plot it for New York, Stockholm, Los Angeles, London, Granada, Rome, Perth, Cape Town, Delhi, Dhaka, okay, Chennai. Okay, and when you start thinking about, well, how could this be deployed in society? I went crazy because it's every aspect of our life involves water. Household use, business, industry, government, remote areas, emergency use, personalized water, real estate, okay, because people are not going to live in the city anymore. They're going to want a place outside the city. Now they can have their own water, independent of the grid. Okay, so it's maybe water harvesting is a real estate company, not a water harvesting company. Okay, seriously, we want to give water independence to the world. Water is a basically human right, and I think this technology will give each of us water independence because we have a device that does not have to be plugged into the grid. And if you really want it plugged into the grid, you can do that. but we can harvest water, and I showed you the numbers, without energy input, just sunlight, or plugged into the wall and getting water that way. So you will have water independence, clean water that could be used for drinking, could be used for agriculture, you don't have to mineralize it, could be used for other things. Well, it took us 25 years to get here. Okay, I've spent, let's say, most of my adult life working on this. Okay, never mind all the hard work as a child. Okay, doing my homework and memorizing poetry and solving math problems and everything since I was 4 years old. So I basically spent my whole life working on this. And it's terrible. Okay, it's terrible. Of course, I enjoyed it, but it's terrible when you think what AI could do, right? The fact is that AI could shorten this span by a lot. So we would be very silly not to invest in AI so that developing the next generation of materials that society needs doesn't take 25 years and somebody's whole life. That we can do it with the aid of AI. So this is now my passion. We are trying to develop the digital discovery cycle. And I really give a lot of credit for my colleague who's here today, Professor Jennifer Shays, who's the dean of a new college in UC Berkeley, dealing with data science and AI, for introducing me to AI and for compelling me to start thinking about AI. And once we started collaborating, then I was hooked. And we want to develop together, we want to develop the digital discovery cycle. And we didn't wait at all. And like I said last night in my acceptance speech, you don't have to wait for the ideal conditions. Just do the experiment, start working. And that's what we did. We designed what we call the digital discovery cycle, and we are already using this cycle, deploying robotics, image recognition, building data sets, and modifying machine learning algorithms so that they're chemistry intelligent to make new materials. And here are the results. Here is a field, a subfield of MOFs that we invented. I didn't talk about it in 2006. And it's a well-farmed area. Many people have worked on this. It's not possible to make new materials, you would think, because many people work in this and it's all the new stuff has already been done. But we wanted to take on this challenge and see whether AI could lead us to making new materials, even in this highly farmed area. Well, the results are here. In the black is the line. This is the machine learning algorithm results, is the line that humans, my students, can do. And the blue is what AI can do. Okay, so it does better. It does a little bit better. And a little bit better in chemistry is great, right? That means that instead of discovering one material every 5 years, I'm discovering a material every week or every month. And that material could solve the next societal problem. So here are the materials that, using that cycle, we were able to make. Many of them I would look at and say, well, all right, that's obvious. But some of them are not obvious, even to an expert, that they could be made. And these are the ones that are appearing in this kind of cycle. Okay. We started a little bit late, so I need 1 more minute. Okay, 1 more minute. I want to finish up to show you something that is even easier than the generative AI cycle that I just showed you, and that is using LLMs like ChatGPT to simplify what we're doing in the lab and speed it up. And that's the work really led by Zach Zhang, who's one of our students. And here, Zach and others in the lab have used ChatGPT to do text mining. Okay, so just by simple prompt conversational language, just like when you Google something, you put that into ChatGPT, and you can start mining the literature for various things. You can even mine images. They even designed a ChatGPT supervisor, so that instead of me going to the lab and saying, well, you should try this and you should try that, this might work and that might not work, they get ChatGPT to guide them to how to make materials and how to characterize them. Even molecular editing for water sorption or for water harvesting, they even designed a research group, everything that a new student, a researcher needs to go from the beginning of making material to applying it and getting the properties that they want could be done with ChatGPT. So, because of the time limit, I just want to say that it is possible for us. We showed that you can take 250 papers and get ChatGPT to tabulate all the experimental conditions appearing in those papers with greater than 90% accuracy. And some of the inaccuracy came from misstatements in those papers. Okay, and so now, with the research group, for example, I told you it takes a long time to make a cough or a moth. It took us 25 years to develop the chemistry. Well, here is a compound that we thought would be very important for water harvesting from air. And the students, instead of spending 3 years making this compound, using ChatGPT, they were able to do this in 2 weeks. Okay, they started off here with nothing, and then by experiment 84, they were already getting crystalline material and the material that they were targeting. So 3 years to 2 weeks is not bad. Okay, we can use the rest of the time to do other things, other great things. Okay, so because of the time limitation, I'm going to end there and conclude and say that reticular chemistry creates materials with precision, and that AI is helping us in, we already have good devices, good materials for carbon capture, but we're going to need even better, right? We have the best materials for water harvesting and CO2 capture today, but we're going to need even better in the future. And so AI will help us get there. And this is an important aspect for humanity, is that many of us, like myself, science changed our life for the better. So how many of us out there have no opportunity because they can't plug into science? So AI for reticular chemistry allows this bar to be lower, entry bar to be lower, so that everybody can plug in. And everybody can begin the process of developing their mind or developing materials for various applications to solve problems in their own locale. I want to also acknowledge these students whom I may not have acknowledged during my presentation, acknowledge the funding agencies, and I want to thank you very much for choosing me for the prize, and it's been a pleasure to be here and an honor for me. Thank you very much.
Thank you very much to Professor Yaghi. Thank you. Please take your seat. Thank you, Professor Yaghi. Thank you. Please take your seat. And now we would like to invite back to the stage Professor Liu to give us the conclusion.
Thank you. Thank you very much, Professor Yaghi, for your very wonderful explanation of the basic science behind reticular chemistry, and your explanation, your description of many of the wonderful applications of moths, coughs, which are very important for us to build a sustainable future. And also thank you for reminding us or to give us a sort of new horizon for material research, bringing AI into collaboration with particular chemistry. It is rare that a person, a scientist, invented something and afford his fellow scientists, fellow researchers, to have the confidence to enter the field, to follow him. And Professor Yaghi has done it. As far as I know, as of today, hundreds or even thousands of researchers have followed Professor Yaghi's step, getting into reticular chemistry, making thousands, tens of thousands, new moths, calves, trying to solve different problems. That's really a unique situation. And Professor Yaghi has accomplished that. Before I end, I like to bring up another aspect of Professor Yaghi. Professor Yaghi founded a foundation called Berkeley Global Science Institution, in which he designed, he developed unique mentoring programs for hundreds of young researchers from countries in the global south to start their own research careers and to do the research in their own country, including Jordan. Scientists, young scientists from Jordan, where Professor Yaghi was born. Ladies and gentlemen, this is in the true spirit of sustainable development. Let's salute Professor Yaghi.
Thank you very much to Professor Liu for the conclusion. Thank you. Ladies and gentlemen, this concludes the Laureate Lecture for Sustainable Development. Our laureate, Professor Yaghi, has to leave now for the press conference. Let's give him another warm round of applause. Thank you so much for your wonderful lecture today.